Today's topic is a technique that you can use in a GCMS system that allows you to reduce your analysis time significantly. It's called LPGC or vacuum. We see in mass spec there is interest in speeding up the analysis. We want to have better sensitivities, more analytes in one run, but also robustness is of course very important, especially in a routine lab, and techniques should be able to work with any type of GC mass spec system. We see out there, of course, chromatography companies, they want to make the best columns to separate the most peaks. But also, if you have a detector like a mass spectrometer, you can use that also for separations. The peaks that elude together, if you can separate them out by the MS, that is also possible. So the solution is a combination of both column selectivity as well as mass spec selectivity. So if we want to speed up in mass spec, there are different ways. Most easy would be, well, move to hydrogen as the carrier gas. Use the same column, about 2 times higher velocities, and that should work. However, the flows in mass spec are often limited by the pump capacities. There's a safety aspect, there may be a spectral bias if you run hydrogen in the mass spec. It's also reactive, and your peaks are very narrow, so you need also a detector that have enough sample rate detection. So the other thing is that if you move from helium to hydrogen in an existing mass spec system, it needs several days to stabilize to get rid of the hydrocarbon grounds. The other thing we can do, we can use a shorter column with a smaller ID. So let's, for instance, use a 10 times 0.1. I can go 3 to 4 times faster. Oh, that's interesting. Also here, there are challenges. There are robustness issues because these 0.1 columns contaminate quite fast, so it needs regular maintenance. The flows are very small, and for injection you need to transfer a part of the sample into the column. Significantly lower loadability that may impact separations. Thin films become activated much faster, which again needs maintenance, or you have to use guard columns. Also here, very narrow peaks, and also for best application you need fast programming options. Okay, we can go another way. We can trade in some resolution for speed, and here we have also several options. We can use the same column and just run it at a higher velocity. Yes, we can make a translation, and what we see here is, we need 12 mils per minute, a high capacity vacuum pump. That's going to be a challenge. And those volumes, the focusing is also a challenge. You need high inlet pressures, but then also very narrow peaks, again high sample rate for my detector, and fast programming options. So also a little bit challenging. Now let's go to a shorter column. So replace the 30.5 for a 10 meter. I can go even 5 times faster. Well, that's pretty cool. However, I do need to have sufficient pressure drop. Yes, my mass spec is on the vacuum, and I like to have a positive inlet pressure. And you see already here, I have already a very low inlet pressure, 0.38 psi. That also means that those low pressures, you cannot really use split flows. The pressure setting is not good enough for that. You need high sample rate detection system also, because you have narrow peaks, and you cannot really trim the column because then your pressure becomes really too low to work with. Also, high temperature programming option is required. Option C is going for a wide bore column. And now if I operate it at reduced pressure, I can go 3 to 4 times shorter. Now how can you operate a 0.53 in a mass spec and still work with the normal flow rates? Well, that's where LPGC comes in. Yes, vacuum gas chromatography. So this technique basically can be used in any mass spec system that uses a vacuum. So only not in the APC IMS systems. They work with atmospheric pressure. This technique of vacuum separation was already known a long time ago. Yes, already around the 60s, they knew already that if you reduce the pressure in a column, you can go very fast. Now in 2000, it became very practical because the restriction concept was introduced. So what is that basically? Well, you're going to use a 0.53 column, you need a restriction, and you need a column coupling device. You use the same injection port. We have the restriction, then the coupling, then the separation capillary, which is 0.53, and that goes straight into the mass spec. That was invented around 2000, and Varian had a patent on that, but they let it expire in 2007, so the technology is open for anybody. Now the proof of concept was also done in the same year. We used a 10-meter metal column and squeezed one end in the restriction, and if we put restriction on the back in the mass spec, we kept 29 minutes retention time. We reverse the column and we keep the conditions the same. The analysis time is much faster, and you get exactly the same chromatogram. So this really works. Basically what happens is that your Van Diemter curve, with FID it looks like this, and if you run it column in a vacuum, in a low pressure, that curve moves to the right. So you have very high optimum velocity. So opportunities, fast separations. Yes, you get short analysis times in mass spec, higher sensitivity, very high capacity, high elutability, peak width that can work in any mass spec, lower elution temperatures. I can elute 50 to 80 degrees C lower, and I will have also lower bleed. Then you can use all the standard injection techniques. It's a robust system, yes, high capacity and inertness because it uses a thicker film. And you can also coat these columns with different phase chemistries. So Mastowska already published in 2001 that with this technique can very easily go faster, yes, and go even more sensitive. Here is chromatogram for Lahote, and we see here in 2015 220 analytes in less than 10 minutes. So that's typical what you get with the LPGC column. Analysis times well below 10 minutes. So Lahote proposed then an optimized solution for this new technique, and the only extra consumable that you need is a ferrule with a 0.8 millimeter internal diameter to connect the column with the mass spectrometer. So the analytical column, it's a 15 meter, 5% diphenyl phase with a 1 micron phase. The restriction is 5 meters, 0.18. Then there's an integrated transfer line there of 1 meter. I'll get back to that later. And unique connector, the seal-tight micro union. So restriction is 5 meters, 0.18. That's of a well deactivated capillary. This length also gives you good focusing in a splitless injection, but it also will act as a guard column. Yes, you can cut pieces of this column without that you immediately find problems with the vacuum. The connection is made by the seal-tight union, very good technology. Yes, that gives you a good seal also with when there's vacuums involved. It's also very low in weight, so there's very little risk that columns will be disconnected if you send them around the world. Analytical column, 5% diphenyl phase, yes, 15 meters, 0.53, the 1 micron film. High capacity, very robust, yes, and these columns are efficient, inert, and can be used to very high temperatures. So the analytical column in the LPGC is basically only 15 meter 0.53, and it will deliver around 30,000 plates. And that's also what we do here. Yes, we are trading in some efficiency for speed. And in case that peaks co-elude, I'm going to use the mass spec for the deconvolution. So we combine here the two options we have, the column selectivity, and when needed we need the mass spec selectivity. Now there's also an integrated transfer line. That is, at the end of the column, the stationary phase is removed. Now why? That part is always heated, yeah, transfer line. And if there's no phase, your mass spec will stabilize faster. You can even use lower transfer line temperatures because, hey, there's no retention there. There's only a deactivation. Also, when you inject water air, which you always do when you inject sample, the absence of stationary phase also gives results in no hydrolyzation of that phase. So also here adds to the sensitivity of your system, and of course it's all integrated, no connections, no. So if you run some organochlorine compounds, you see if you use oven programs of 30 degrees per minute, you can run already within 10 minutes. But if you have a system that has a higher heater capability, you can go much faster, say even within 4 minutes. Here's a typical comparison. Conventional analysis, 23 minutes, and with the LPGC we can do this within 7 minutes. Another example, 63 pesticides, the conventional method, again around 20 minutes, and we move to the LPG solution in over 8 minutes. And look at the very nice peak shapes. Even very complex samples, 209 pesticides in strawberry, also nicely separated within 10 minutes using the LPGC solution. So typically that's what you will see. Analysis time will never be 10 minutes. Now to test the robustness, we took a catcher's extract of spinach. Yeah, it's known to be quite challenging. This was the separation of the first injection. Peaks 1 and 2, resolution factor 1.00. After 500 injections of this extract, now this is without any maintenance in between, the resolution is still 0.96. Well, those are nice values. I really appreciate. That means you can expect a long lifetime. And that's even without maintenance. Now for good integration you need about 7 to 8 data points per peak. Now the peak width that the LPGC kit produces are 1.5 to 2 seconds broad. So they can be measured by any mass spec system. Now if you have a mass spec with a faster data collection rate, like a TOF, you can consider to use even faster programming or operate at higher flows if you have a vacuum pump that can allow that. Now important is setting up the method, because it's a different technique and the restriction defines the flow, not the column. So the method needs to be set up using the restriction dimension. So column length 5 meter, column ID 0.18. And here you're going to set the flow, and which is typically between 1 and 2 mils per minute. Since the restriction is also acting as a guard column, I can cut pieces from the restriction. But since the restriction also defines the flow, if you cut 20 centimeters off, your flow will increase from 2 to 2.08 mils per minute. And your analysis time gets even shorter. Now, if you want the same analysis time and the same flow, there are different ways to deal with that. Most easy is just set the column length from 5 to 4.8 meters in the method setup. Another way is just buy some restriction tubing and cut 20 centimeters off and connected in front of your analytical restriction of the LPGC. And now the restriction is again 5 meters and your retention times will be. You can cut quite a significant length of that restriction before you run into serious trouble. Yeah, look, even if we cut 2 meters off, we still have inlet pressure of almost 30 kPa. We get into trouble if we cut 3 meters off. So around the 2 meter, your inlet pressure will get too low. So you have to realize then that you have to replace restriction. What you can do, you can buy a new restriction and couple it, or you purchase a new pre-connected unit. Now to make that coupling, yeah, there are videos on the YouTube that will guide you through this. So the differences of this new technology is you have a lower plate count, yes, but it's mitigated by your selective detector. Yes, if you have isobaric components that elute close, you may have to choose a different selective phase. You have higher bleed from thicker film, yeah, but the elution temperatures are significantly lower, yes. Greater potential for leaks, there is a coupling, yeah, but the column becomes pre-connected, so you do not have to use the coupling yourself. And it's a very stable product that has a very long lifetime. Rapid oven heating is preferred, yes, that gives you the shortest lifetime, so like to use 220 volt instruments, or you can also reduce the oven size. You can buy a kind of pillows for that, accelerators, and then you can use faster oven programming. Now the setup, the GC method, you have to use the restriction dimensions, and of course the connection with the detector is done with a ferrule that fits a wide bore column of 0.53, and that means you need a 0.8 millimeter ID. Now this technology has been widely explored by Stephen Lahote in the area of pesticide analysis, so many publications, and he definitely is 100% convinced that this technique is the fastest and robust way to do the GCMS analysis. 2 years ago, publication was also done in LCGC with the title that says everything. There's no time to waste. Low pressure GC mass spec, LPGC mass spec is a proven solution for fast, sensitive and robust GCMS analysis. Here's a result from a German customer that did 2 different temperature programs, one with 30 degrees programming and one with 45 degrees programming, and you see already the enormous win in analysis time if you use the higher program rates. Shimadzu also published some data on these columns and the unique things that you can do with the LPGC approach. Now, what are the limitations? Well, basically, if you have a column with 120,000 plates, yeah, you get this kind of separation and runs 24 minutes. You easily can do this 3 times faster, yes, and you still have baseline separation with the LPGC MS solution. However, if you have a separation like this, just baseline resolution, like the benzofluorantines on a 17 type phase, yeah, if you move to an LPGC dimension, you have a problem with the separation because you will never be able to separate these isomers. And for the mass spec, all these peaks are exactly similar. So you need to use a much more, let's say, selective stationary phase to be able to separate these kind of bars. So LPGC is a new great tool that allows you to do fast and robust MS analysis and maintains or even increases sensitivity. Typical 3 to 4 times faster. You can do it with your present instrumentation. The only difference is the ferrule at the MS transfer line, yes, and setting up the method. Then there is an optimized column developed out there. Stephen Lahote did a great job that has an integrated transfer line which helps you to stabilize your system much faster. It's a very versatile solution and you can use this kind of solution, basically for any GCMS application, as long as there are no isobars eluting very close together. If you need 100,000 plates to separate isobars, yes, you cannot separate them with the present LPGC technique unless you have a very, very selective phase in place in the same column format. Okay, with that, I'd like to thank you for your attention.